Tenacious coders and challenge champions, it's Prof. G, and in our last lesson you were challenged to leverage several printing techniques that you'd learned so that you could write code that made the TO area in the terminal act like a sensor plotter. So let's show a solution for that challenge. If you need to review the challenge, here it is, but it's described and demonstrated in more detail at the end of the last lesson. I hope it went well for you. Let's get into that plotting goodness. Also, friends, just before we get started, a quick shout out to the ever so kind Todd Kurt, aka Toddbot, who gave me the idea for this challenge. Todd does all sorts of great things for Adafruit. He has a wonderful CircuitPython tip sheet at this URL. I've also included a link in the lesson's description for you to check that out. He's also a hardware creator and has some cool products for sale on Tindy. He's also the co-host of the Bootloader podcast, along with the incomparable Paul Cutler. You can follow him on the socials. Do follow him, and if you post questions in Adafruit's Discord, I wouldn't be surprised if he drops a bit of knowledge your way. And now to begin, plug in that Circuit Playground board, Bluefruit or Express. Start up PyCharm. If you're new here, welcome. You may want to check out the prior lessons in the playlist to see how we got to this point. And with PyCharm open, I'm going to start fresh by deleting everything that's in code.py, and we'll add a comment up top that says print-plotter.py. We'll import the libraries we need, board, time, analog IO. Then let's set up the light sensor on our Circuit Playground board. We'll call that light_sensor, and we'll set it equal to analog IO, our library up here, .A analog I in. That's the class that acts like a blueprint to create an analog input, and we want to go to the class factory, so we'll include parentheses, and we're going to pass between the parentheses board dot and in all caps light, the location of the light sensor on the Circuit Playground boards. Then let's set up some of those variables that I'd mentioned in the challenge. So we want to create a line_length, and we'll set that equal to 90. You could have used a different value in here if you wanted to. 90 works fairly well for my font size. Then underneath this, we'll say sensor_max, and we'll set that equal to 65,535. That's the maximum value that you can get back from the light sensor. And now we should really calculate how much space we'll have after we print the sensor value on the far left. And that value is going to print with a comma separator and with an extra space after the value, which acts as a border between the sensor value and the plot value. So essentially what we're trying to figure out is how much space do we have for plotting. So why don't we call this plot_length, and we'll set it equal to line_length minus, and let's get a length of the sensor max reading with a comma in there. So we'll say len, L-E-N, for the length, and in between parentheses, we're going to create an F string. So we'll say F, and then in between double quotes, in between curly braces, sensor_max, and we want the comma to be in here, so we'll say colon, comma. That's our format specifier to include comma separators. And we'll subtract one more from this. That one more represents an additional value that we're going to take away from the overall line length to represent a single space border we want between our sensor reading and the line plot. Then we'll create our while true statement down here. And what we want to do is we want to call a function that we haven't defined yet, but we're going to call print_plot. And we're simply going to pass into this light_sensor.value. Then under this, I also suggested that we slow down the sensor reading, so we'll do that with time.sleep, and in between parentheses, 0.05. Now in the challenge, I mentioned that we should create a function called print_plot that passes in the sensor value. So above while true, we'll define the function with def space print_plot, and between parentheses, we'll pass in sensor_value, colon. And sometimes it's most helpful to set up what your final result line is going to be and then work backward. That's what I'm going to do here. I'm going to say, okay, what do I want to print on each line? So I'll print an F string in between double quotes and in between curlies is first going to be my sensor value. So sensor_value, I want to format that with colon, and I'm going to put in the fixed value 6 here and then comma. But I want to get rid of that literal 6 value, and we'll show you how to do that in just a bit. Then after this F string, I'll say plus spaces, and spaces will be a variable we'll define in just a bit, that will hold all of the spaces that we should have before the star that represents the plot value for our sensor reading. Then I'll say plus the string asterisk, which concatenates the star to the end of all of my spaces. So I don't like having this literal 6 value in here as part of my print format specifier. So let's create a variable to hold that, and let's have it calculate regardless of what our sensor max will be. So above plot length, why don't we create a value, and we'll call this, how about value underscore length, since this is going to be the length in characters of whatever we print out as a sensor value. And we'll set this equal to, it's essentially this calculation that I have right here. So I'm going to highlight this length with the F string here for the sensor max, cut it out, paste it in after the equal sign, and then where this used to be in the plot length equation below, I'm just going to put in the variable value underscore length. Then down here in the last line of my print underscore plot function, I'm going to replace the sixth with open and close curlies, and I'm going to pass in my value underscore length value. Cool. So if I have a new sensor that has 1,000,000 as the sensor max, this will still calculate the appropriate size that I need for my sensor value, and we'll subtract that from whatever my line length is. Next up, let's calculate our spaces. So spaces will equal the string of an empty space, so that's just double quote space, close double quote, multiplied by, and let's build out the number of spaces we need. Now remember, we're going to enclose this in an integer, or an int, open and close parens, because if we didn't do that, we'd probably get a float with decimal values, and we can't get a fraction of a space. So that's why we convert this to an integer. And we'll say in between these parentheses, sensor underscore value times, and in between another set of parentheses, plot underscore length divided by sensor underscore max. Now I'm going to also surround the whole int portion of this equation here in another set of parentheses, and inside that parentheses I'm going to subtract 1, and that -1 from the inside of this is to take away the single value represented by the star, which is part of my plot. I don't just want the number of spaces in here, because if I calculated the number of spaces I need like this and then added the star to the end, there's a possibility that I might be 1 over the line length. So I want to subtract 1 in here because I'm going to add one more character at the end, the star. Whoops, don't forget the 1 in here, it's -1. Ooh, and I almost forgot, we want to add a single space between our sensor value and our spaces. That'll just make sure that there's not a star that's touching the numbers for the sensor value. So now let's get in the terminal and we'll launch TO, and up top I'll make sure that I've saved. And whoa, our sensor readings are plotting. Let me move my circuit playground around so we can see some changes. And this looks perfect. And you can see if I cover up my sensor, the plot moves to the left and I have smaller sensor values. Those values are right justified with commas when needed. And there's a single space border between the smallest plot values and my print plot line. So this is nicely responsive. It's looking good. You can play with this more if you'd like. But what I'm going to do now is close the terminal and save this to my CircuitPython School folder as print-plotter.py, and then I'll close the extra tab so I'm back at code.py. Now note that there's a lot more that we could do to create reusable code. We could have created this as a module for import, but I think there's enough in here for our current position in the course. I hope you like the results that you've gotten, that you think that this is neat, and that you're learning a lot. As always, there's a lot more big learning to come, lots more hardware to work with. Until then, keep hacking.